Hello everyone, this is Firoz Nadaf. In this video, we will see the analysis of flanged beam. First, we will try to understand what is the meaning of analysis in this context. Analysis means we are required to find moment capacity of the section. We are required to find how much moment it can resist, how much bending moment the section can resist. To find the moment capacity, what will be given to us? A complete section will be given to us. The cross section will be given to us. In case of flange, they will give you the width of the flange, that is BF, depth of the flange, that is DF, overall depth of the section, that is capital D, and BW is width of the web. And they will also give you the reinforcement details, how many number of bars that has been provided in the section, what is the diameter of the bar. Means a complete design will be given to us, and they will ask us to find the moment capacity or to analyze the structure. In this design problem, in this analysis problem, the very first step is to locate the neutral axis, where neutral axis lies, whether it lies in the flange or it lies in the web. Okay, so accordingly we have four cases. Case number one, when neutral axis lies in the flange, means xu, the depth of neutral axis is less than df, the depth of the flange. It lies in the flange. Okay, it lies in the flange here. Okay, this will be your xu. Okay, case number two will be when the neutral axis lies in the web. Neutral axis lies in the web, and the design is balanced. This is your case number two. Case number three is when the neutral axis lies in the web, and the design is under reinforced. And case number four, same, neutral axis lies in the web. It lies in the web, and the design is over reinforced. Okay, so we have four cases. In this video, we will see case number one, and we will also solve the problem with regards to case number one. Case number 2, 3, 4 we will see in the next video. Okay, now we will locate the depth of the neutral axis, whether it lies in the flange or it lies in the web. Now you see, you cannot find depth of the neutral axis to locate neutral axis. Okay, because you have different formulas. If neutral axis lies in the flange, you have different formula of xu. If neutral axis lies in the web, you have different formula of xu, that is depth of the neutral axis. So you cannot find the depth of the neutral axis and then indicate where neutral axis lies. So what we have to do, we have to locate the neutral axis without finding the depth of the neutral axis, and we can do that by using two formulas, that is FTC. This is total compressive force of the flange beam. Total compressive force total compressive force and FTS, total tensile force of the flange beam. Now you see what will be given to you to find FTC and FTS. A complete section will be given to, I already told you. They will also give you the grade of concrete and grade of steel. Grade of concrete and grade of steel. Whether you are using M20 grade concrete, M30, they will give you. Whether you are using mild steel or HYSD bars of different grade, they will also mention in the problem. Okay, So what is FTC? In some book, FTC is denoted as total compressive force of the flanged beam, or it is also denoted as flanged force. Flanged force. And this FTS is denoted as web force. So what is FTC? FTC, the formula of FTC is FTC equal to 0.36 FCK BF into DF. 0.36 FCK is the characteristic strength. It depends on the grade of concrete. For M20, the value of FCK is 20. BF is width of the flange, and DF is depth of the flange. So this is the formula of FTC. FTS equal to 0.87 FY AST, total tensile force or the web force in this particular context. Okay, so by the given data we can find FTC and FTS. If FTC is greater than FTS, after calculating the value you have to compare. If FTC is greater than FTF, then you can say that neutral axis lies in the flange. By the way, case number A is very easy to solve. But case number 2 to 4 is complex, and we will see how it can be solved. But case number A, when the neutral axis lies in the flange, analysis becomes very easy when neutral axis lies in the flange. Okay, so this is the comparison. FTC equal to FTS. Neutral axis lies at the junction between the flange and the web, means it lies just below the flange. Okay, neutral axis lies at the bottom of the flange. Neutral axis lies at the bottom of the flange. Okay, and if FTC is less than FTS, neutral axis lies in the web. And when neutral axis lies in the web, already we have seen that here we have three cases from case 2 to case 4. As I already told you that in this video we will refer to case number 1, that is neutral axis lies in the flange. So that is the case when FTC is greater than FTS. So when neutral axis lies in the flange, we will have to consider the beam as a rectangular beam. We'll have to consider the flanged beam as a rectangular beam of size BF into capital D, and we have to do our design and analysis by considering this size of the rectangular beam. Okay, so how you will find the depth of neutral axis? Already we know the formula of depth of neutral axis, that is total compressive force equal to total tensile force in case of singly reinforced rectangular beam. That is total compressive force equal to total tensile force. Total compressive force is 0.36 FCK BXU. I am referring to the rectangular section in limit state method. This is total compressive force, which is equal to total tensile force, that is 0.87 FY AST. Okay, so this is about rectangular section. Now here in the flange beam, the size of the rectangular section is BF into capital D. So instead of B, you have to take it as BF. Okay, so accordingly you have to modify the formula. XU equal to 0.87 FY AST divided by 0.36 FCK BF, width of the flange. Okay, after getting the depth of neutral axis, you will have to find XU max, limiting depth of neutral axis, and XU max value, XU max formula depends on the grade of steel. We have different formulas of XU max by D depending upon the grades of steel. For Fe250 it is 0.53, For Fe415 it is 0.48, and for Fe500 it is 0.5, sorry, 0.46. Okay, so just it will be given in the problem which grade of steel you have to use, and small d, if small d is not given, you can find small d, that is effective depth of the beam from overall depth, just knowing the diameter of the bar. Okay, so you will be able to find xu max. Then you have to compare xu and xu max. Xu is less than xu max, then the design is under enforced. And this is very important to to identify which type of design is given, whether it is under enforced, over enforced, or balanced. Accordingly we have different formulas of moment of resistance. Okay, so xu greater than xu max, then the design is over enforced, and xu equal to xu max, design is balanced, or you can say limiting section in case of LSM. Okay, if xu is less than xu max, you can use the value of xu max. If xu is less than xu max, if xu is greater than xu max, you cannot use the value of xu max. Means, sorry, xu, you cannot use the value of xu if xu is greater than xu max. See, xu max indicate maximum depth of neutral axis. Above it, it cannot be used in the design, in the analysis problem. Okay. Now we can find the moment capacity, the factored moment of resistance, or the ultimate moment of resistance for case 1 when the neutral axis lies in the flange. So we generally mu equal to cu into lever arm or tu into lever arm. So you may choose to find from compressive force, from total compressive force, from total tensile force. It depends on you. Okay, so if you want to find with respect to compressive force, so already you know the total compressive force for the flanged beam. Instead of B, we have to take BF. 0.36 FCK BF XU. Okay, yeah, this is with respect to under enforced. The design is under enforced. Okay, into lever arm, if you know the analysis of, or you analysis of stress block diagram in LSM, you will get to know that what is a lever arm in this case. Small d minus 0.42 XU. So this is with respect to total compressive force, moment of resistance from total compressive force. You may also choose to find total compressive force with respect to total tensile force, 0.87 FYAST. This is total tensile force into lever arm. Lever arm is D minus 0.42 XU. Okay, so you can choose any formula, or you can use both the formula. So whichever is lesser, whichever which by which formula you are getting the lesser value, that will be your moment of resistance of the section. Okay, so we will see one problem. A T-beam of effective flange width 1200 mm. So they have given the width of the flange, that is 1200 mm, and thickness of the slab is 100 mm. By the way, thickness of the slab is nothing but thickness or the depth of the flange. Okay, so depth of the, depth of the flange is 100 mm. Width of the rib is nothing but width of the web. This width is 300 mm. Instead of overall depth, they have given effective depth. Effective depth, small d equal to 560 mm, and they have also given how many number of bars that they have provided in the design, that is 4 number of bars they have provided in the design, and the diameter of that bar is 25 mm. They are asking us to find the factored moment of resistance, means the capacity of the section with respect to limit state method, and they have given the grade of concrete and grade of steel that is used in the design. Okay, so in this problem, first we have to locate where neutral axis lies, whether it lies in the flange or it lies in the web. To do that, we need to find FTC and FTS and compare FTC with FTS. FTC, the formula of FTC is 0.36 FCK BF into DF. BF width of the flange, DF depth of the flange. So FTC equal to 0.36 into 20, grade of concrete is M20, BF is 1200 mm and DF is 100 mm. So the value of FTC you will get after the calculation is 864 kilonewton. 864 kilonewton. You will get in Newton, you can convert that into kilonewton. Okay. FTS FTS it depends on, okay, so formula of FTS is 0.87 Fy AST, 0.87 into 415, the grade of steel is 415 into 4 bars of pi by 4 into 25 square. AST is given. We need to find the area of steel that is provided in the design. So the value of FTS is 709 kilonewton. So here FTC is greater than FTS. Neutral axis lies in the flange. Neutral axis lies in the flange, and we have to do the analysis. We need to find the moment capacity, and we since the neutral axis lies in the flange, uh, the flange beam will be considered as a rectangular beam of size BF into capital D. We got to know that the depth of neutral axis lies in the flange. Now we need to find the depth of neutral axis. What is the depth of the neutral axis? And now we can use the formula. As of now we know that it lies in the flange. So the formula of XU is XU equal to 0.36 FCK BF, okay, divided by 0.87 FYAST. Okay, so XU equal to 0.36 into 20 into 1200 divided by 0.87 into 415 into 4 bars of area of each bar, that is pi by 4 into 25 square. So XU value you are getting here after the calculation, the value of XU is 82.07 mm, which is less than the depth of the flange, and now we can verify that actually it lies in the flange, because XU is less than XU is less than the depth of the flange. After getting the value of XU, we are required to find XU max, and XU max by D, it depends on grade of steel. The grade of steel that is given in the problem is Fe415. For Fe415, XU max by D is 0.48. Okay, so XU max equal to 0.48 into small d, that is effective depth of the beam, is given in the problem, 0.48 into 560 mm. XU max equal to 268.8 mm, and after calculation of XU max we have to compare with XU. The value of XU is something around 80. XU is less than XU max, and we can conclude that the design is under reinforced. Okay, so we have two formulas when the design is under reinforced. For a singly reinforced beam, we are required to find MUR, ultimate or factored moment of resistance. The formula for that is 0.87 into Fy AST into lever arm D minus 0.42 XU. Okay, 0.87 into 415 into 4 bars of area of each bar, that is pi by 4 into 25 square, into D is 560 minus 0.42 into the value of XU is 82.07. Okay, so by this formula you are getting MUR equal to 372.65 kilonewton meter. You'll be getting in Newton mm, and you can convert that Newton mm into kilonewton meter. Alternatively, you can use the formula with respect to the compressive force. Already we have talked about that. Mu are equal to with respect to compressive force, total compressive force into lever arm, 0.36 FCK BF into XU into lever arm, D minus 0.42 XU. And when you substitute the value of all these parameters, you will be getting the same value, 372.65 kilonewton meter. Okay, thank you for watching this video. Thank you very much. If you have any question, you may ask in the comment box.